Okay, we continue. So the questions we're asking, we have to ask ourselves is is substance X really in it? Does the lake really show complete mixing behavior? Because if it does not, meaning you have variations there in the concentration, which could affect your calculations. Are the reported concentrations in factory wastewater correct? Okay, maybe so your initial concentrations, are they really correct? Or maybe there's some errors there. Does the inflowing river contain pollutant X? So you find that maybe the inflowing river, you may write it off as not containing pollutant X, when in actual fact, maybe it may actually be carrying pollutant X from some other effluents that it may have collected upstream. Or are there other pollution or natural sources, okay, which could be emitting this pollutant X other than those two factories that you have? So those are some of the questions that you may have to revisit. Okay. So addressing these questions will result in a better system description, and mass balance analysis is a fundamental analytical tool. So like we mentioned earlier, mass balancing helps us understand where our material is going and if we're efficiently and whether or not we're using it efficiently. Okay. And it also helps us in this case of the lake, help us understand, isn't it, the concentrations of these pollutants in the lake or in whatever river body. So not water body, sorry. So not long ago, there was that truck carrying sodium hydroxide that plunged into the Kampinsa River some months ago. Maybe some of you may be aware, or maybe some of you may even work for the same company. Uh, what do you think were the first things that, if you were the environmental officer there, what was going to be your main interest in that particular incident? You have sodium hydroxide, truck plunging and spilling all that sodium hydroxide into the lake. So what would be your point of interest as environmental officer working for assigned to that, or an inspector under ZEMA? What would you be interested in knowing?
Yes, madam.
Yes.
I think the first thing is to have knowledge of the substances the practice carry. After knowing, when you conduct tests, which ones are harmful.
You conduct a what? Sorry, I can't get you clearly.
Test. You test the water for possible pollution.
Okay. So you said you're testing the water, but before that, what are you doing?
You know what the substance the truck is carrying.
Okay.
What exact substance the truck is
Mm-hmm.
carrying. Then you conduct water chemistry test.
Mm-hmm.
Test if it's been polluted, what levels of pollution, concentration.
Mm-hmm.
As well as the quantity of what is being spilled.
Okay. So what is your mass balance going to consist? Are you going to need to use the mass balance?
Yes, the mass balance equation apply.
Okay, so what are you looking at basically? Give me a scenario of how you do it or what you'd be interested in. What will consist of your mass balance?
So we name it's sodium hydroxide, you say.
Uh-huh.
Sodium hydroxide will be given let's say X, it will be our X in this case.
Uh-huh.
Then there's water involved.
Uh-huh.
Then the quantities of sodium hydroxide, of course, those will be in the equation.
Okay.
Then among the assumptions, we say there was no production. Because we know the track, the pollutant is only coming from the track.
Okay.
So our production is very zero. Then we determine what is in the water.
Mhm. Okay, any other thoughts? Any other thoughts on what the mass balance will consist of? Okay, so one thing as you come on site, isn't it? You understand that sodium hydroxide, isn't it? Is what kind of a chemical is it from what you know? Is it a harmful one? It is, isn't it? So it can actually cause harm to aqua life, isn't it? Aquatic life also, such as fish, for example, the most common. Okay. So whatever aqua life that you have there could be affected by this. Okay, so maybe you want to understand how much of this sodium hydroxide has come in, isn't it? That one you have to determine. And then you need to determine, so what has come in? So you're trying to determine accumulation, what has remained inside these fish. Okay, so something has come into this water and there was fish in there and there were crocodiles or whatever it was that was there. Okay. But you need to understand how much of it has been left in the bodies of these um, species. So you calculate what came in, isn't it? Minus what left plus production, isn't it? That gives you your accumulation. So that will give you a rough idea as to how much has remained. So now what left in this case, how do you think we determine what left? It's a river flowing, isn't it? So meaning that water is moving, okay? It's not stagnant, it's not a lake. It was a Campisa River. It was actually water that was moving from point A to point B at a certain flow rate. Okay, so maybe your primary interest here is to know what damage that sodium hydroxide spill could have caused, okay, on the biodiversity in that river or that part of the river there. So you'd use a mass balance weight try and determine how much could have accumulated and stayed in that place. Okay, and from there you try and analyze and determine whether or not what has accumulated in that place could cause adverse effect to aqua life in that particular area, or it's too small or too little to be actually regarded as insignificant concentration. Any other thoughts how you do it? Okay, we move on. Well, let's look at a problem here now that involves steady and non-steady state problem and data. So we're going to understand here once more what we mean by, we've understood what we mean by steady state, but we're going to now look at the problem that involves both steady and non-steady state in one question. Okay, so here we're told consider a well-mixed tank with a volume of 1 cubic meters filled with water with the following conditions. Okay, so there's this tank, 1 cubic meters, okay, that has been filled with water with the following conditions. Condition 1, at time is equal to 0, a solution of salt A is continuously pumped into the tank, okay, as tank influence. A solution, remember it's not just plain salt, so it's a solution of salt A. It's continuously pumped into the tank. I hope we're imagining with me. Do we have the sketch here? We have the sketch down here. Okay. Then at T is equal to 0, also a reactor effluent. Okay. Sorry about that. I seem to have been logged out. Let me just quickly share the notes again. Okay, I hope we've understood point number 2 here, condition number 2. I hope it's clear. At time is equal to 0 also, a reactor effluent is established. Effluent salt concentration is 2 grams per liter. Then condition number 3, the influent and effluent flow rates equal 10 liters per second. Okay, so I don't need to explain again why Fi is equal to Fl. It's pretty clear, isn't it? So when Fi is equal to Fl, what does it mean?
Madam.
Uh-huh.
Doc.
Yes.
Hello.
Yes, I can get you. Go
Yes,
ahead.
Doc. I think for my sake, for my sake, I just beg that you start over example 1.3 because the previous ones I missed out a lot because first and foremost I joined very late and I've been having poor network here. So just for this example, please, if we can just start it together.
Okay, we'll do it. So which one is this one now? Example 1.2 or 1.3? Oh, this one that we just started. Actually, we're just there. We've not even covered anything. So you're talking about this one, right?
Either.
Steady and non-steady state problem and data.
Yes, I'm talking about this one, though the area one I missed. So I don't know, but what I'm requesting for is at least on one example, if I can just be like full-time part of the system.
Okay. Okay. All right. Okay. So let's go. Okay. I understand what you mean. We'll go through example 1.2 for your sake. We just run through it. At least I know a number of people understood. So we just run through it together. Okay. All right. So this is example 1.2. We're asked to calculate the pollutant concentration in a lake that receives wastewater from 2 factories. So 2 factories are bringing in wastewater into a lake. The lake surface area has been given and the depth has also been given. The lake is also fed by a river with a flow rate of 10,000 cubic meters per day. So there's 2 factories bringing wastewater. Okay, factory 1 is bringing wastewater into the lake and also factory 2 is bringing wastewater into the lake. So aside from these 2 factories, there's also a river that is flowing through this lake also. But this river does not contain pollutant X. We've not been given. So we assume that it has 0 concentration of pollutant X. So we assume that CI is equal to 0. However, for F1 and these concentrations, these values have all been given. So concentration of pollutant X has been given through pollutant X in this stream has been given. Concentration of pollutant X in this stream has also been given, or in this effluent has also been given. Okay, so apart from that, what are we also told? We're told that this lake, since the volume is constant, isn't it? So it means that when these start coming in, what happens? This lake is full and it automatically now at the same instant starts spilling out. Okay, so it's spilling through this channel, okay, an outlet here, which we're calling FL at the rate of FL. And the concentration we're calling CL, the concentration of this pollutant X that has come in through these 2 factories. Okay, so meaning on the outlet there also we'll have this CL here happening. Okay, so the question is asking us to find the lake, the pollutant concentration in the lake. So we're asked to find the pollutant concentration in the lake. So pollutant X concentration within the lake. So what we know from last time and what we discussed last time is that when there's an overflow, what does it mean? It means that concentration in the lake will be same as the concentration on the outlet here, what's leaving. So the concentration of what's inside here will be the same as what's leaving here. And we have those assumptions that we made to help us understand that. Okay, so we looked at two, so this system involves two species rather. So you have polytan X here, where it's supposed to find the mass balance for polytan X, and also you have water, because this polytan X is coming in a mixture of water, also in a water solution rather. So you have this aqueous solution of polytan X joining here. So meaning we have to account for all the waters plus the river that is bringing in pure water. So we have to account for all the water that is entering here, okay? Which is the same, using the same principle for our mass balance, which is what comes in minus what leaves plus production is equal to accumulation. So accumulation is equal to what comes in minus what's leaving plus production of whatever it is that's coming in. Okay, so for polytan X, what do we know? Change in volume times concentration over change in time ultimately should give us 0. Okay, so what do we have here? What's coming in? So this is coming from the river, coming from factory 1, coming from factory 2, minus what's leaving, that's the outlet. Outlet's volumetric flow rate multiplied by concentration of polytan X at the outlet plus production of polytan X, if any, in the lake. The lake, remember, is now our reactor here, which is basically the same thing that's happening here. Then when it comes to water, what do we know? Change in what? Density times volume over time. Okay. Which will give us what? Density multiplied by flow rate of the river. So this is for the river. This is for the factory 1. This is for factory 2 minus outlet plus production. So remember, our other assumption is that we have constant density also here of water. The density of water will remain at 996 and it will not change, so at 1000. Okay, so it remains constant. We adopt the same here everywhere. Okay, so which is which brings us here now, change in density multiplied by volume. Remember, volume also of the lake is constant. So we have that equation there. Accumulated water mass is equal to that. Okay, so now these are the system equations that we came up with. It's fully mixed, meaning concentrations of polytan X here at this point in the lake, at that point in the lake, and this point in the lake are all going to be equal. In short, concentrations of polytan X at any point in this lake should be equal because there's homogeneous mixing in the lake, homogeneous distribution of dissolved substances. And then what else do we know? The lake has a constant volume, okay? The lake volume is not expanding and it remains constant. Therefore, dV over dt, change in volume over change in time, gives us 0. Water density is constant. I've explained this one already. There is no production of water within the lake. That is, P is equal to 0. Okay, then the water balance here now, FL, so the volumetric flow rate at the outlet will be equal to what's coming in. Remember, there's overflow now. The lake was already full of water when these factories started discharging into it. So simply it means that what came in now began, the flow rate of what was coming was equal to what was leaving, or what is leaving is equal to what is coming in terms of flow rate, what's coming in. Okay, that's why we have FL is equal to FI plus F1 plus F2. Okay, so this one is now what? This is for water, mass balance for water. Okay, and then now in terms of flow rate, it gives us this. Okay, so when you cancel out the density on both sides, this is what you have left. Okay, remember, bearing in mind that dV over dt is equal to 0. So this is what you have left. The river water entering lake Fi does not contain X, remember? So meaning this particular gives us 0. Why? Because concentration here of polytan X in the river is equal to 0, because in this river there's no polytan X. The only place where we've been told there's polytan X contained is in factory 1 emissions and factory 2 emissions. There is no production of X in the lake. That's the second, the fourth assumption. The fifth one is there are steady state conditions with respect to X and with respect to water. Okay, so DVC X over DT will give us 0 when we say steady state conditions. So meaning you have 0 here, and here you have 0 because of this. This one remains as it is, as it is, as it is, and here there's no production of X in the lake, pollutant X in the lake, so you have 0 here. Okay, so from here now, this is what we're going to carry forward. From here, we're going to be interested in this guy here. Why? Because this is outlet concentration. Okay, and earlier we know that where there's overflow, it means that concentration here in the reactor will be equal to concentration on the outlet. The example of when you're carrying a cup of tea and you spill some of it out, the concentration of sugar in the tea that remained in the cup will be equal to the concentration of sugar in the tea that spilled on the floor on the table under that assumption. Okay, so that's how we're going to get our CXL. So when you put CXL on this side of the equal sign, it becomes positive, isn't it? So you have this coming here, and then you have this remaining, isn't it? So you simply divide CXL by FL, this other side by FL, so you have the FL here. So this is basically what happened here. So this is F2CX2. Ignore this. This is not necessary. It's not supposed to be here. Okay, so again, we remember we said FL will be equal to Fi plus F1 plus F2 because there's overflow. And that's how come we have the values there. We're not given this in the question, but we're given all these 3 values. So we make use of these 3 values to come up with this. The top values, the concentrations here of pollutant X in factory 1 and factory 2 are given, plus the flow rates for effluent from factory 1 and effluent from factory 2 are also given in the equation. So we simply multiply, divide accordingly, and we get 13 milligrams per liter as our answer. Are you able to get me? Someone is saying they're cut off. I hope I'm being heard by someone at least.
Yeah,
Yes,
the
clear.
network is quite poor today.
Yeah, it's quite
At some
poor.
point,
Yes,
at
the
some
challenge, huh? It's a challenge. Okay. Moving forward, what do you think because of this network challenge? Are you okay with a pre-recorded lecture, or we just still try and work around the network at least so that you're able to ask questions within the lecture? Or I just do a pre-recording where I'll be clear throughout? Which one? The goal ultimately is to ensure that you've understood without hiccups.
We can work with what we have at the
I
moment.
I think if we can have a pre-recorded, which we can download. I don't know if we can have like a link on YouTube or something. Then we have sessions where we are not clear, then we ask questions. I don't know.
Okay, I'll try and do a pre-recorded session in future, then we see how it works. I think ultimately my goal is to ensure that you've understood. It can be quite a challenge when someone is speaking and they're breaking, and you're not able to understand everything. It's a bit hard to connect to concepts also. Anyway, so let's work with what we have for tonight. We'll try and see how. Where you're not clear, please feel free to ask. Okay, I'm willing to repeat whatever it is that I may have said that you may have missed. Okay, let's come to our steady and unsteady state problem data. Okay, so we are here. I hope, was it Gershom who asked us to go back a bit? I hope now you've understood.
Yes, it's Gershom, but at
Okay.
some point he was cut. I think he missed
Oh
some part
no.
I'm
of.
following, Doctor.
Okay. He's saying he's following. Okay. I know. What's important is that you're following. All right, so let's come to our number now here, our example here, 1.3. Consider a well-mixed tank with a volume of 1 cubic meters filled with water with the following conditions. So at T is equal to 0, a solution of salt A is continuously pumped into the tank. So you have a solution of salt A being pumped into this tank as tank influent. So it's coming into the tank. So it's influencing into the tank, if it's such English. At T is equal to 0, also a reactor effluent. So effluent meaning is what? What's reactor effluent in this case? Is it MI or ML?
It's ML.
Yes. So ML is established at the same time. Huh? So then we're given the influent salt concentration, which is 2 grams per liter. Okay. Third condition is that the influent and effluent flow rates are equal to what? 10 liters per second. So I was saying in a case where you have Fi is equal to FL, it means that there's overflow, isn't it? That FL is actually overflow. We've been talking about this. So that's why the flow rates are also equal, 10 liters per second for both influent and effluent. Derive an equation for effluent concentration. So what's effluent concentration? What's leaving, isn't it? So that's going to be our CL, right? If we're going to call our salt A, so it's going to become our CAL. That is what we're being asked to find, CAL. So this question is very similar to the one that we just looked at. Okay, so we define our system boundaries are what? The reactor walls or the walls of this tank. Okay, so the walls of this tank become the system boundary, as you can see here. Okay, so you have salt solution coming in at T is equal to 0. You start now pumping in salt solution at a given or at a known concentration of the salt. We've been given salt influent as 2 grams per liter. Okay, what else do we know? That's the input. So we've been given the flow rate for the input, volumetric flow rate, and we've also been given what here? We've been told that this flow rate, input flow rate, is equal to output flow rate, which is equal to 10 liters per second here. The influent and effluent flow rates equal 10 liters per second. Those are the 3 conditions. Okay, so the system boundaries are reactor walls, which are the walls of the tank. So we're supposed to first of all identify all flows, influent and effluent, and identify all concentrations. So which concentrations do we have in this particular case? The concentration of salt A in the influent, so what's coming in, isn't it, becomes our CAI. The concentration of salt A in the reactor, so there's that salt inside our tank. Okay, there's that concentration. And the initial concentration of salt A in the reactor at time is equal to 0. So at T is equal to 0, there's no salt, isn't it? So meaning our CA0 within the reactor, within the tank, will be equal to 0 at time T is equal to 0. Only at this time. Then here lastly, the concentration of salt A in the effluent, which is CAL. This also is a typo. So concentration of A in the effluent is CAL. Okay. So now next step here is to identify all relevant data. Any questions so far on identification of our influent and effluent and concentrations? Are we all clear? Please feel free, if you're not clear, just simply mention and we look at it again. Silence means we're all clear. Okay, we move forward. Now we're looking at what? All the relevant data. So you have volume of the tank remains constant, isn't it? Then you have our
Yes, madam.
CA0, yeah. So you have our CA0 at t is equal to 0, which will be 0. Then you have our CA at different times. So at the dt, a certain dt. So you have dVC A over dt here, which will give us what's coming in, inputs, right? Minus output plus production of salt A in our reactor. This becomes our accumulation. This becomes our mass balance for salt A. Okay, so now formulating the mass balance equations, I think this is becoming simpler, isn't it, as you see this? So you have dVC A over dt is equal to this, what's coming in minus what's leaving plus production. Okay. Then let's try and understand what's happening here. How do you explain this? Can we try and see how we can explain this? Equation 2.9. Look at it carefully and see tell me what you understand from it.
Can I try?
Yes, please.
We're looking at the volume of the tank, which is fixed. The concentration of salt that is given the tank happening at unit time. There's unit time happening.
Continue. Have we lost you?
No.
Okay. Oh, you're still thinking. Please
still
feel
thinking.
free. Take.
Okay, let me think further.
The equation yeah being there, sir. Okay, anyone else to help him while he's thinking? Okay, so we know that volume is not changing, isn't it? It's going to be fixed for the tank, right? But what's changing here? What's changing is what? But we know this will not remain fixed, isn't it? It's the same.
The concentration is changing.
But what's changing is what? The concentration at outlet, isn't it? So at T is equal to 0, outlet there also concentration was 0, isn't it? Then as with time, as you are dosing in that solution into the tank, what's happening? The solution there is beginning to change, isn't it? On the outlets. So initially to be 0.001 grams per liter, it will come to 0. Like to just keep growing and growing. So there's that change in outlet concentration over time, isn't it? As time is moving, this concentration is also increasing. There's that proportionality that comes in. Okay, so I've explained this one. What about this side now? This last part, can I have someone explain what's happening here?
The concentration at the outlet is also fixed there, but what's changing this time around is the volume with time.
Which volume is changing?
The volume at the outlet, the amount, the flow. I don't.
Someone help him. Look at it clear. Look at the next equation to give you a clue. Which volume we're talking about here? Okay, so this is basically from mathematics, okay? Trying to understand this derived equation, isn't it? So this derived equation means what? This one, okay, on the side, right? And it also means this part also on the side, then dV over dt, right? So the first part we have explained, isn't it? Where you remove this one, put it on the side, right? And you have dCl here. And the second plus, so mathematically, okay, this is what it means. So mathematically now it means this is going to be the same as plus this one on the side plus dV over dt, okay? So dV over dt, we know that is going to be 0. Why? Because the volume of the tank does not change, okay? So it will remain constant. So change in volume over change in time will give us 0, okay? It's different from volume multiplied by change in concentration over time. So dCAl over dt cannot give us 0, isn't it? Because we know that this concentration at the outlet is changing, right? Over time, it's actually increasing, provided you keep dosing the salt A solution into the tank. So this will keep increasing. So meaning dCAl over dt cannot be equal to 0 to give you a value, right? However, dV over dt, from our conditions, we know that this one is going to give us a 0, isn't it? Because the volume of the tank is not changing over time, okay? No matter how long you go and come back, the volume of the tank will still be 1 cubic meters. It's not going to expand, it's not going to shrink, nothing will happen, it remains constant. So this gives us a 0. Okay, then what do we know again? Production of salt A gives us also 0. Okay, so from there on, we make a conclusion that V dCA over dt is equal to FICAI minus FLCAL. What's coming in? Input minus output. Because this is 0, so meaning we don't need to include it. We'll say plus 0, but it's not necessary. It's clear already that there's no production of solution of salt A, sorry, in this tank. So volume multiplied by change in concentration, outlet is supposed to be an L here also. AL over dt is equal to what came in minus what left. Okay, so that's the mass balance equation. Okay, so we look at the assumptions now for the system. What are the assumptions? The reactor is ideally mixed. Okay, like I said again, in reality, it's a bit hard to achieve unless you have a mixer there, something to mix everything. Then the salt entering the tank is instantaneously and homogeneously distributed. Also in reality, that's pretty much difficult to achieve. But anyway, number 3 assumption, the salt concentration is uniform in the reactor. Therefore, the effluent salt concentration, which is CAL, T there with T dependent on time, of course, equals the salt concentration in the reactor. Okay, so our 40 minutes is up. We'll be logged out very soon. You just simply click on the link to continue. So the effluent salt concentration, CAL, dependent on time, as a function of time rather, equals the salt concentration in the reactor. Okay, the issue of spilling fruticana from your cup and the concentration remaining the same. This is the principle that applies here also. Therefore, CA as a function of time should be replaced by CAL as a function of time. We agree, isn't it?
Yes.
Okay, so we agree that in the reactor, it should be replaced by this one because it's the same, similar to